And this bracket notation, which is the mathematical notation for quantum mechanics introduced by the great quantum physicist P.M. Dirac. You can have your quantum mechanical system is independent of its representation. But the vector representing the quantum mechanical state of a physical system in a complex vector space of finite or infinite dimension should have a special name to distinguish it from other vectors. So we can call it as a Kate vector, and Kate can be denoted by the symbol which I have shown in earlier. The symbol is like this, a part of a bracket. And we label the quantum state by inserting the level of the state in the middle of the symbol, and the quantum state alpha is written as shown in the screen. So in your Kate vector, you can represent a wave function psi or a wave function or a quantum state alpha as shown in the screen. And the quantum state psi, so quantum state alpha is represented in the Kate as this, and the quantum state psi can also written as Kate psi as shown in the screen, and so on. And this Kate vector is sometimes referred to as the state vector, or just you can say it is state. So we can use these terms interchangeably. After knowing this, let us have some more discussion about the Hilbert space. So the set of all possible state vectors that describe a given quantum mechanical system form a complex vector space, which is called the Hilbert space of the system, and is denoted by the symbol H as shown in the screen. So your alpha, beta, these can be shown in Kate vector as shown in the screen, and these are any two elements of H or a Hilbert space, and the sum of the two elements alpha plus beta can be written as shown in the screen in the Kate alpha plus beta, and is also an element of H. So H is a linear vector space defined over the set of all complex number capital C, and the vector sum is commutative and associative. The vector sum is commutative and associative, and you can have three state vectors alpha, beta, and gamma, and you can write these as like this: alpha in Kate vector alpha plus beta is equal to beta plus alpha, so it is commutative. And similarly, you can write alpha plus beta plus gamma is equal to alpha plus beta plus gamma, so it is also associative. And the product of the state vector alpha with a non-zero complex number C, say C can be 1, 2, 3, 4, anything else, can be written as C alpha, is once again a vector of the Hilbert space. So if a quantum mechanical state of the system is represented by alpha Kate alpha in Kate notation, the same state can also be represented by C alpha, which is in a Kate bracket. So the physical information of the system contained in the state vectors does not change if it is multiplied by a non-zero complex number. And the vector sum is also distributive, so we can write for arbitrary complex numbers A, B, C, and the elements alpha, beta of H as A plus B alpha is equal to A alpha plus B alpha, and C alpha plus beta is equal to C alpha plus C beta, since C is an arbitrary constant. So there exists a unique null vector 0 in Kate, such that for any vector alpha, 0 plus alpha is equal to alpha. So for any element alpha in Kate, there is also an additive inverse minus alpha. So you can write alpha plus minus alpha in Kate is equal to 0 or null vector. Then a superposition or linear combination of two or more state vectors of the quantum system is also a state vector of the quantum system, and hence an element of Hilbert space. So if psi 1, psi 2, psi n are the states of the quantum system written in a Kate vector, then the linear combination psi 1, C1 psi 1, C2 psi 2 plus so on Cn psi n is equal to summation I is equal to 1 to n Ci psi I, where C1, C2, Cn are complex number, and Cn is Ci is the expansion coefficient. And these are C1, C2, Cn, these complex number, and the state psi is a state using this complex number. The state psi is the state of quantum system and the vector in Hilbert space of the system, and this makes the Hilbert space a linear vector space, which you know in your mathematics class. And the dimension of a vector space is the largest possible number of linearly independent vectors, and you can find for the vector space. If there is no such largest number, then we say the vector space has an infinite dimension. And a set of n linearly independent vectors, phi 1, phi 2, phi n, forms a complete basis for an n-dimensional Hilbert space, which I have discussed in your Schrodinger formulation. If any element psi ket of the vector space can be expressed uniquely as a linear combination of these states, so you can write your psi as a C1, phi 1, C2, phi 2, so on, so for Cn, phi n. And this is nothing but summation I is equal to 1 to n Ci phi I for all psi belongs to H. And C1, C2, Cn are complex numbers. And the coefficients C1, C2, Cn of the expansion psi are the components of the state vector psi in the basis phi 1, phi 2, so on and so forth, phi. And this is the beauty of the notation, that in a finite dimensional Hilbert space, the ket vector psi can be written in a column matrix as shown in the screen. C1, C2, so on, so forth, Cn. So when you can write it as a matrix form, then you can use matrix algebra to solve the quantum mechanical problem. Similarly, the bra vector can be represented in a row matrix. The ket vector is represented in a column matrix, and the bra vector is represented in a row matrix. So this matrix algebra will be used to solve the quantum mechanical problem. And in quantum mechanics, we can use both finite and infinite dimensional vector space. So there are different types of bases for Hilbert space. One is denumerable, and where the basic vectors are countable, and non-denumerable when the basic vectors are not countable. And the basic vectors in non-denumerable case are labeled with continuous variable. Okay. Then let us discuss bra vector. So the symbol is like this, as shown in the screen, a part of the bracket. So the label of the vector is inserted inside the symbol. You can have your alpha, beta, psi in this ket, bra vector. So that we can have alpha, beta, and so on, and there is one-to-one correspondence between bra and ket vector. And the bra vector alpha for alpha is alpha ket, and the bra vector for beta is beta in ket, and so on. And the bra vector for the sum of two ket vectors, alpha and beta, is the sum of bra vectors alpha beta. You can write alpha beta shown in the screen in bra or ket. So the bra vector for C alpha is C star alpha, where C is a complex number and C star is its complex conjugate. The bra and ket vectors of a state vector are the transpose conjugates or adjoints of each other. So when psi in a ket vector is a column vector, the psi in a bra vector is a row vector, which I was telling you earlier, and it is the adjoint of psi. So bra and ket are adjoint of each other, self-adjoint. So ket psi can be written as a column matrix, as I have told you earlier, and bra psi is written as a row matrix having the complex conjugate of each values in the ket. If in ket you have a column matrix form C1, C2, so on, so for Cn in bra notation, you have your C1 star, C2 star, so on, so for Cn star in a row format. So we have two distinct vector spaces: the vector space containing the ket vector H and the dual space H star, which contains the bra vector. So your ket psi belongs to the Hilbert space H, and bra psi belongs to H star. And we write the adjoint of psi is equal to, in adjoint of ket psi is equal to bra psi. So where dagger represents the adjoint. Every ket vector in the vector space has a bra vector in the dual space, which is its adjoint, and vice versa. And if the basis in the space of ket vector is phi 1, phi 2, so on, so forth, phi n, the basis in the space of bra vector is in your phi 1, phi 2, so on, so forth, phi n in bra vector. Then your inner product. So I have discussed it earlier, and in bracket notation, it is represented or written somewhere in a different format. So the inner product or scalar product for any two elements, alpha and beta, ket of the vector space denoted by the symbol in a bracket alpha beta, where alpha is represented, alpha is placed in a alpha is placed in a bra, and beta is placed in a ket. So alpha and beta is placed in a bracket, which is a complex number C. So you can have your alpha beta in bracket is equal to C, and the inner product has the following properties: interchanging the role of two vectors alpha and beta ket in the inner product, you can have alpha beta is equal to C, gives us the complex conjugate number C star. So in bracket beta alpha is equal to C star. If alpha beta is equal to C, then beta alpha is equal to C star, and you can write it as alpha beta is equal to beta alpha star. So alpha beta in bracket is equal to 0. It means that either alpha or beta or both are null vectors, or that alpha and beta are orthogonal vectors. And the inner product obeys both distributive and associative properties, and it is shown in the screen. And the norm or length of the state vector is the quantity root over of alpha in bracket, which is a real number. And there can be a overlap between the states. Transition amplitude and probability amplitude can be evaluated as shown in the screen. Then orthonormal basis in quantum mechanics, it is usually convenient to work with an orthonormal basis. With this definition of inner product, we can generate an orthonormal basis for any arbitrary basis which has no special properties whatsoever. And Gram-Schmidt orthogonalization process, which I've discussed in mathematical physics class, is the formalism by which you can have your orthonormal basis, and it is shown in the screen. And a Hilbert space is a finite or infinite dimensional linear vector space with an inner product defined on C. Then your linear operators in Hilbert space. We have discussed linear operators in Schrodinger formalism. So the formal definition of a linear operator in Hilbert space. So a linear operator is an instruction or mapping that transforms a vector psi of the Hilbert space H to another vector psi dash of H. And you can write O cap psi is equal to O cap psi in S state vector, that is equal to psi star, and O cap denotes the linear operator, and we use the same notation for linear operator that we have used quantum mechanical operators earlier. And the arbitrary complex number a comma b and elements alpha beta of H can be written as O cap a alpha b beta a which is nothing but a O cap alpha b O cap beta. So O cap vector when operated over alpha and O cap vector operated over the state beta will give you eigenvalue of that operator. So for any two linear operators Q cap, O cap and Q cap and a vector alpha, we define the sum of linear operators as Q O cap plus Q cap alpha is equal to O cap alpha plus Q cap alpha. And for any two linear operators O cap and Q cap and a vector alpha, we can define the product of the linear operator as O cap Q cap alpha is equal to O cap Q cap alpha in vector notation, vector space notation. An operator O cap is also can be null operator when its value is 0. You can have also your unit vector or identity operator. You have also inverse operator, commutator, algebra, projection operator, alpha beta. You can have projection operator, you can denote it as P cap alpha. Okay, so this is all about operator mechanism. A Hermitian or unitary operator or unitary operator, which I have discussed earlier. And it can be half O cap plus O cap dagger plus half O cap minus O cap dagger. You can write O cap as this. So Hermitian operator is nothing but half O cap plus O cap dagger, and anti-Hermitian operator half O cap plus O cap minus O cap dagger, O cap minus O cap dagger. So this is in the PM Dirac formalism. Similarly, unitary operator U cap plus U cap dagger is equal to I cap, unitary operator. Then eigenvalues and eigenvectors in Schrodinger formalism, you have your differential equation, and when it is operated, suppose E cap, it is a differential. It is a differential equation. E cap can be represented in a differential form del by del t, I h cross del by del t. So when it is operated upon a wave function psi, you will have your energy eigenvalue. Similarly, in Dirac notation, A cap psi, when psi is in a psi is represented in a ket vector in a vector space, and when A cap is operated over a psi, then you have A psi, where A is the eigenvalue of that wave function psi or state function psi. So here the difference is here there psi can be written in a psi is a function, complex complex representation, and there is the operator is in a differential notation, and here it is the psi is in a matrix representation, and when A cap is operated in that Dirac formalism, you will have A multiplied by psi in A eigenket. So A is the eigenvalue. So your psi is an eigenket. You can say write it as eigenstate or eigenvector of the operator A cap with an eigenvalue alpha. So if there are more than one eigenkets corresponding to an eigenvalue A, this we can say that degenerate, multiple values possible. If it has only one value, you can say it non-degenerate, which you have discussed in your harmonic oscillator and hydrogen atom problems. So similarly, you can have a eigenvalue spectrum for a set of all eigenvalues of an operator, and then your characteristic equation, how you can solve it and how you can have the values. There you have the differential equation, and here you have a matrix representation. Then eigenvalues of Hermitian operator, omega cap psi n is equal to omega n psi n, and you can have the inner product as shown in the screen, and you will have your when Hermitian operator is operated, then you can have the values. Then eigenvectors of Hermitian operator you can see in the screen, orthogonality, orthonormality, so on and so forth. Then commutating operator, unitary operator, these you have discussed in quantum mechanics, but there it was in a differential equation form, and here it is in matrix form. Then in infinite dimensional Hilbert space, we have a non-denumerable basis, which we have discussed earlier or defined earlier. The basic states will be represented by a continuous variable minus alpha minus infinite smaller than z smaller than infinite. So then we have discussed many quantum mechanical problems in Schrodinger formalism, and here we have there you have the Hermitian operator, and that will describe the observables. And here you can have a overall picture. One is Schrodinger picture, another is Heisenberg picture, and Heisenberg equation for different quantum mechanical problem and how to solve it. So observables and measurement. In classical mechanics, you have an operator. In classical mechanics, you have observable, and in quantum mechanics, operator will give you the value of observable in terms of eigenvalue. Now we now can state some postulates related to quantum mechanical observables and measurements. So postulate one is every observable of a physical system is described by an operator that acts on the Kate vectors that describe the system. So you know psi when written in a Kate vector is shown as the screen. It is written like this. So for a observable A, the corresponding operator may be denoted by A cap, and when A cap acts on the state vector psi of the system, you can write A cap psi is equal to psi dash. So in general, the action of the operator changes the state of the system, So from psi to psi star, from psi to psi dash. So every act of measurement causes a disturbance in the system. However, there are some state vectors called eigenvectors that are not changed by the action of operators. For these states, we have A cap psi is equal to A psi, when A cap is the operator, psi is the state vector, and small a is the eigenvalue of the operator. And in the next postulate, you can have your, if A is the observable corresponding to the operator A cap, then the result of the measurement of the observable capital A for the physical system can only be one of the eigenvalues of A cap. Since the result of the measurement on a system can only be a real number, the eigenvalues of the operator corresponding to the observable must be real. And hence observables in quantum mechanics corresponds to Hermitian operator, and we have discussed it earlier during our discussion in Schrodinger picture. So if phi 1, phi 2, so on and so forth, phi n are the set of eigenvectors of a Hermitian operator A cap with the eigenvalues small a1, small a2, so on and so forth, small a n respectively, the result of a measurement of A has to be one of these eigenvalues a1, a2, so on and so forth, an. And clearly, if the system is in the state phi I, the outcome of the measurement would be ai, and the reverse is also true. If the outcome of the measurement is ai, the reverse is also true, and if the outcome of the measurement is ai, the system should be in eigenstate phi I. And in a finite dimensional Hilbert space, the eigenvalues of a Hermitian operator are discrete. They are not continuous. And the eigenvectors of the Hermitian operator form a complete set and span the Hilbert space. This set of basis vectors, phi 1, phi 2, so on and so forth, phi n, is called the eigenbasis of A cap. So if you assume that phi 1, phi 2, so on and so forth, phi n are an orthonormal basis, that is in bracket phi 1, phi I, phi j, which is nothing but del ij, where del ij is the Kroneker's delta. Any arbitrary state psi can be written as psi state is nothing but summation I is equal to 1 to n ci phi I, where ci are the complex coefficients. So let us assume that all states of the system are normalized. So you are in bracket psi is equal to 1, that is norm 1, and summation I is equal to 1 to n ci modulus of ci square, where ci is equal to in bracket phi I psi. If now measurement of A is made on the state psi, the probability that the outcome of the measurement is the eigenvalue AI is modulus of ci square, or you can write it as in bracket phi I psi square. Okay. And the next postulate is, when a measurement of an observable A is made on a normalized state psi, the probability of obtaining an eigenvalue AI is given by the square of the inner product of psi with the eigenstate phi I of A cap, assuming that the eigenstates form an orthonormal basis. So now, because we have ci square summation I is equal to 1 to n is equal to 1 for an arbitrary state of system, at least one of the values ci is non-zero. Therefore, when a measurement is made, at least one of the results a1, a2, so on and so forth, an must be observed. We now define the expectation value of the observable A with respect to the state psi, and you can write A cap, expectation value of A cap is equal to in bracket psi A cap psi. This is the average measured value of the observable, and using the definition of the identity operator, whose value is 1, or you can write it as I cap. So you can have your expectation value of A cap is equal to summation I is equal to 1 to n AI in bracket phi I psi whole square. So we must not be confused between expectation value and eigenvalue. The expectation value, which is a average value and can be any real value in the range of the eigenvalues of A cap. The result of the single measurement is one of the eigenvalue. So if you measure the energy of an electron, it will give you one of the eigenvalue of the energy. But if you take 5 values of energy at different time or at different positions, you can have the average value by using the formula of that, and it is nothing but expectation value. So this is different. Your average expectation value is something an average value, but the eigenvalue is the measurement of one single measurement, result of the one single measurement. Then von Neumann measurement postulate 4. If on measuring A for a system in a generic state psi, a result AI is obtained, then the state of the system immediately after the measurement is phi I in K, and it is collapse of the state vector. So we have a system, formally we have a system in generic state defined in the eigenbasis phi I of an observable A cap. So as psi in cat is equal to summation I is equal to 1 to n ci phi I, when a measurement is made of the observable A corresponding to the operator A cap, the generic state psi, which is a linear combination of all the eigenstates of the eigenbasis, collapses to one of the eigenstates of the eigenbasis. So you can write it like this: psi is equal to summation I is equal to 1 to n ci phi I. After the measurement, it will be phi I, and it collapses. So you can say that collapse of the state vector takes place on account of an interaction of the system with the external world through the act of measurement. Before measurement, it exists. After measurement, it collapses. You can also look upon it as an updation of our knowledge of the state of the system as a consequence of the outcome of measurement carried out on the system. So this can be represented pictorially as shown in the screen. Measurement of observable A. After the outcome of the measurement, what are the states of the system? So you must understand that the last two postulates are not the same. The third postulate says that if repeated measurements are made on identically prepared system, which means that each of the systems is characterized by the same case psi, the different outcomes of the probabilities mentioned in the third postulate. But the fourth postulate, on the other hand, means that if an observable is immediately measured again on the same system, the outcome must be the same as the first measurement, and therefore the system must be in the corresponding eigenstate. So we may assume that the state into which the initial state of the system transforms must be connected to the initial state of the system. And since the outcome of the measurement is always one of the eigenvalues, and after the measurement of the system moves into one of the eigenstate, it stands to reason that the initial state, which can be any general state, must always depend on the eigenstates of the operator. Since any general state is expressed in terms of a complete set, we conclude that the eigenstates of an observable form a complete set. The association between quantum mechanical observable and a Hermitian operator therefore hinges on the existence of complete set of eigenvectors called the Hermitian operator. And we have discussed completeness concept in Schrodinger formalism. So a quantum mechanical observable must be a Hermitian operator which has a complete set of eigenstates, be it in finite or infinite dimensional Hilbert space. An operator that does not satisfy these conditions does not represent an observable. So we can address the following concern: are all Hermitian operator with a complete set of eigenstates physically observable? And the answer is in principle yes. Yet there may be Hermitian operators which do not correspond to meaningful physical quantities or may not be measurable experimentally. In that case, while the measurement is feasible theoretically, it may not be possible in practice. The theory of quantum measurement remains one of the most debated topics in quantum mechanics, and most of the debate is centered around the von Neumann measurement postulate. The basic assumption in the measurement postulate is that the physical system itself remains intact through the experimental process of measurement, and whatever changes takes place in the state of the system does not destroy the system itself. There are many experiments in the states where the state survives. For example, Stern-Gerlach experiment, and which we'll discuss later on. But there are experiments where it does not. For example, suppose you design an experiment to measure the number of photons in an electromagnetic field. Usually this is done by observing the photons in some detecting device. And when the detecting device observes the photon, its state collapse. It does not exist in your measurement after the measurement, which means that the photons are destroyed, removed from the system by the measurement. So if we started with some n photon state, after the measurement, we end up with a 0 photon state. For such a situation, there is a generalized measurement theory which is different from what is discussed now. So in Stern-Gerlach experiment, after the experiment, the state survives. But when in absorption experiments where the photon is absorbed by the detecting device, the system collapses. Then compatible and incompatible observable. A pair of observables A and B corresponding to the operators A cap and B cap respectively are compatible if the operators A cap and B cap commute, which means that the commutator of A cap and B cap is 0, and it is written in commutator bracket A cap B cap is equal to 0. And it is incompatible if the operators A cap and B cap do not commute. So the value of the commutation operation is not equal to 0. It is non-zero. The reason for this classification will become evident when we look at the consequence of a sequence of measurements of different observables on the same physical system. So if we measure two observables, A and B sequentially in some physical system in an arbitrary state psi. Suppose we first measure the observable A. The outcome of the measurement is one of the eigenvalue of A cap. Let us say small ai, and the state of the system immediately after the measurement is the eigenstate corresponding to the value ai, which is phi I. So let us assume for now that A cap has only non-degenerate eigenvalues. Now suppose we carry out the measurement of the observable capital B on the same system immediately after the measurement of capital A. At this point, it becomes relevant whether A and B are compatible observables or incompatible observables. And if A and B are compatible observables, the operators A cap and B cap commute, and therefore, we have discussed it earlier, the operator A cap and B cap have a common set of eigenvectors. For non-degenerate eigenvalues, any eigenvector phi I of the operator A cap with an eigenvalue ai, small ai, is also a simultaneous eigenvector of the operator B cap with an eigenvalue say bi. So if the measurement of capital B is carried out immediately after the measurement of capital A, we would get the value small bi, and the system will continue to be in the state phi I. If we immediately follow up the measurement of B with another measurement of A, we would certain to get the value ai, eigenvalue. So the second measurement, which is the measurement of B, does not destroy the information regarding the first measurement, that is measurement of A, and this can be shown pictorially as shown in the screen. Measurement of compatible observables A and B and the outcome. And this is clear when A has non-degenerate eigenvalues. What if the observable are compatible, but the eigenvalues A are degenerate? The result of the measurement A may be the k-fold degenerate eigenvalue AK, and the state would be a linear combination of the degenerate eigenstates of A corresponding to the degenerate eigenkate xi I. So you can write I is equal to 1 to k Ci xi I. Now, if B is measured, one of the eigenvalues of B cap would be obtained, and the system would move to one of the states of the linear combination with the appropriate eigenvalue. Now, if A is measured again, you would still get back the value AK. So for compatible observables, irrespective of whether the eigenvalues are degenerate or not degenerate, the measurement of B does not destroy the information regarding the measurement of A. It is possible to determine both A and B precisely at the same time. An accurate measurement of one will not destroy the accuracy in measurement of the other. But this is not true for compatible variables. So in canonical conjugate variables, suppose your X and P, E and T, if you measure accurately X, then you cannot measure precisely P. So it collapses. If you measure T accurately or precisely, then you cannot measure E simultaneously, and it will collapse. So now let us consider what would happen if A and B are incompatible observables. So let us label the eigengates A cap and B cap by phi I and xi I respectively. The outcome of the measurement of A is one of the eigenvalues, say A cap, and say AI, that is eigenvalue, and the state of the system immediately after the measurement is phi I. So since the operators do not commute, they do not have simultaneous eigenvectors, phi I is not an eigenstate of B cap. The outcome of the measurement of B following A would be some eigenvalues of B cap, say B small bj, and the state of the system would be the corresponding eigenkate of B cap xi j. If we now carry out a measurement of A, you could get any of the eigenvalues of A cap, not just the one you got in the first measurement. So for compatible observables, the second measurement scrambles the result of the first measurement, and we can no longer determine both observables exactly. So you can write the outcome of the state pictorially, measurement of incompatible observable A and B as shown in the screen. Many of the observables we measure are incompatible, like position and momentum, energy and time. Okay, so these are incompatible. So in a uncertainty principle, we deal with incompatible observables or canonical conjugate variables. Okay, then generalized uncertainty principle, which will be discussed for the measurement which are not incompatible. So given an operator a cap, and this on uncertainty principle we have already discussed in Schrodinger picture. So given an operator a cap, we define another operator del a cap. So a cap minus expectation value of a cap. So what is it? So it is as shown in the screen. So del a cap square is equal to a cap square minus a cap whole square. The in expectation value for notation. So the expectation value del a cap square is called dispersion of a cap. You may find it referred to as the variance or mean square deviation. And your del a is equal to root over of del a cap square is called the root mean square deviation and is an estimate of uncertainty in the measurement of the observable A. So let us calculate del a cap square for any eigenstate of a cap and say phi I. So you can write your del a cap square is equal to 0 and a cap phi I is equal to ai square. So clearly, if the state in the question is eigenstate of the operator a cap, then del a cap square is expectation value, its expectation value is 0. If it is not, the dispersion is finite. As we will show subsequently, any two Hermitian operator a cap and b cap must satisfy the following inequality for any given state of quantum system. Del a cap square, it's the expectation value of del a cap square multiplied by expectation value of del b cap square is greater or equal to 1 by 4. Your in commutator bracket a cap b cap, its expectation value and its square. So it is a quantitative measure of how the combined uncertainty of measuring two observables relates to their compatibility. So let us start by defining the action of del a cap and del b cap on the state psi. So you can write del a cap psi is equal to alpha and del b cap psi is equal to beta. Then since a cap b cap are Hermitian operators with real expectation values, your del a cap and del b cap are also Hermitian operator, and you can write del a cap dagger is equal to del a cap and del b cap dagger is equal to del b cap. And therefore, your alpha in a state vector can be written as psi del a cap dagger, which is nothing but psi del a cap. So by solving it, you can have the final expression del a cap b cap, its expectation value is equal to half commutator bracket, its expectation value del a cap del b cap plus half expectation value of del a cap del b cap. So by solving it, you will arrive at del a del b greater or equal to half expectation value of modulus of expectation values a cap b cap. So this is uncertainty principle for certain pairs of observables. The uncertainty principle derived in more general, but because it relates the product of mean square deviation of any pair of Hermitian operator. And the general uncertainty principle has the following consequences. For any two compatible observables A and B, del A, del B greater or equal to 0. Therefore, A and B can be simultaneously be measured with arbitrary precision, and there is no restriction on the accuracy of simultaneous measurements. For any two incompatible observables A and B, del A, del B must always be greater than or equal to a positive definite quantity. So inherently there is a limit to the accuracy with which A and B can be simultaneously measured. Thus, for every pair of incompatible observables, we have a Heisenberg-like uncertainty principle. So it may be position, momentum, energy, time, or anything else. Then quantum dynamics. The time evolution of quantum system described in time-dependent Schrodinger equation in a differential equation form I h cross del psi by del t is equal to minus h cross by twice m del square psi by del x square plus b psi, and where psi is the wave function, and in operator notation you have h cap, e cap, so and so forth, and we have discussed it. And in Schrodinger picture, we know that the initial state of the system psi when t is equal to 0 is equal to psi 0. And using Schrodinger equation, you can uniquely determine the quantum dynamics of the system. If the Hamiltonian operator of the system does not have an explicit time dependence, which also means that operator x cap and p cap do not have time dependence either, and only the state vectors are evolving with time, this is called Schrodinger picture or of quantum dynamics. And we have discussed it in the earlier classes. Similarly, what is Heisenberg picture? In this picture, the evolution of a system, we do not study the time evolution of state vector, but rather we look at the time evolution of the operators which represent the physical observables of the system. This reflects the idea that the evolution of a system with time, what is actually observed in experiment is how the different observables change with time. And the operators in this picture are assumed to evolve with time according to the rule A cap H, which is a function of T, is equal to E cap dagger A cap U. The state of the system does not change, and we can write psi H T in a ket vector is equal to psi H 0 ket is equal to psi 0. So A cap H and psi H are used to represent the operators and the state vector respectively in Heisenberg picture. This is to distinguish these from corresponding operators and wave functions in the Schrodinger picture, which are written in A cap and psi respectively. So in a Schrodinger picture, you have the differential equation, and in Heisenberg picture, you have the matrix formalism, and you can solve the quantum mechanical problem accordingly. Then your Heisenberg equation of motion in a bracket format. Heisenberg equation for simple harmonic oscillator, we have solved it using Schrodinger formalism differential equation. Here, you can solve it by using the bracket. Okay. Then you have the choice of the basis. And these are the worked out problems. You can go through it. Then simple harmonic oscillator. In Schrodinger picture, we have solved simple harmonic oscillator problem using Schrodinger wave equation, which is a differential equation. And here you can solve it by using operator formalism. And we shall discuss your creation and annihilation operator, the number operator, and other uncertainty product. So you can see simple harmonic operator problem can be also solved using your Dirac notation or Heisenberg picture. The Hamiltonian operator of the simple harmonic oscillator can be written as H cap is equal to P cap square by twice m plus half m omega square H cap square. So in Schrodinger picture, you have your minus h cross square by m del square by del x square plus half m omega square x cap square psi n is equal to E n psi n, where n is the eigenenergy and psi n is the eigenfunction of the nth energy eigenstate of the simple harmonic oscillator. So in Dirac notation, you can write it as h cap n is equal to E n n. N is ket state, which is in a matrix. Ket matlab it is a column matrix. So this equation is of general validity and does not confine itself to any specific representation. So this is specifically when operator and states are represented in position representation. So here you have A cap can be written as 1 by root over 2 h cross m omega multiplied by m omega h cap plus I p cap, and A cap dagger can be represented as 1 by root over 2 h cross m omega multiplied by m omega x cap minus I p cap. Now you can express a x cap and p cap in terms of A cap and A cap dagger. And substituting these in the equation, the Hamiltonian operator H cap can be expressed as H omega A cap dagger A cap plus half. So you know the commutation relation between position and momentum H cap and P, that is I H cross. So similarly, you can have your A cap dagger is equal to 1 in commutation. So H cap can be written as commutator of H cap with A cap will give you minus H cross omega A cap. And you can say have your H cap A cap dagger is equal to H cap omega A cap dagger. So you can calculate minimum energy from this. So now you can consider an arbitrary eigenkete E of H cap corresponding to the eigenvalue E. So let us consider the action of A cap on E in Kate formalism. So you have your Kate alpha is equal to A cap E. And by taking the adjoint, you can write bra alpha is equal to E A cap dagger. So alpha in bracket will can be written as in bracket form in inner product form your E and your A cap dagger A cap. So A cap dagger A cap can be written as H cap by H cross omega minus half, and this is so you can write H cross omega alpha in bracket is equal to inner product is equal to E minus H cross omega by 2 E the inner product of the energy eigenfunction. So you know that the norm of the state vector is always positive. So your alpha and E in bracket are positive definite quantities. So you can write E minus H cross omega by 2 is greater or equal to 0, and you can write E is greater or equal to H cross omega by 2. So you can see that minimum possible values of n eigen energy of the linear harmonic oscillator is H cross omega by 2, and it is non-zero. So at this stage, you cannot say that the minimum energy is half H cross omega, as we have found in the Schrodinger formalism. So you can only say that the minimum energy could be half H cross omega or anything greater than this. So you can write E is equal to H cross omega by 2 after your alpha in bracket is equal to 0, and you can solve the equation. So your Kate alpha is equal to 0, and you also say that A cap E is equal to 0 and E is equal to H cross omega by 2. So this is 0-point energy. So expectation value of the Hamiltonian operator, which is written as H cap average value. This can also be written as average value of the Hamiltonian operator. This is nothing but 1 by 2 twice m psi p cap square psi in bracket plus half m omega square in bracket psi x cap square psi. So you can define Q as x cap psi and P is equal to p cap psi. So x cap and p cap are Hermitian, and you can solve this. And your H cap expectation value of H cap will be nothing but 1 by twice m in inner product of P and plus half m omega square inner product of Q, and which is greater or equal to 0. So the expectation value of energy of the simple harmonic oscillator is always non-negative. It is positive, or okay, or it is not 0. It is non-negative. It is positive or 0. So energy eigenvalues you can also calculate. H cap A cap which is nothing but your A cap H cap minus H cross omega A cap. For the eigenkete E of H cap corresponding to the eigenvalue E, so you have H cap A cap E is equal to E minus H cross omega A cap E, the inner product. So you have an equation earlier, and in the eigenkete provided it is not 0. So you can consider the case when A cap E is not equal to 0, and in this case for the equation your H cap A cap E is equal to E minus H cross omega A cap E. We can draw the following conclusion. If ket E is an eigenkete, then A cap E is also an eigenkete. If ket E is corresponding to the eigenvalue of E, A cap E corresponding to the eigenvalue E minus H cross omega. If however E is equal to E0 is equal to half H cross omega, we necessarily should have A cap E0 is equal to 0, as otherwise we'll have states with energy less than half H cross omega, which is not possible, as half H cross omega is the lowest possible value of E, as we have derived from Heisenberg picture. Further, if A cap E is an eigenkete, then A cap square E is also eigenkete corresponding to the eigenvalue E minus 2 H cross omega, provided A cap square E is not equal to 0. To see this, write the eigenkete A cap E as E dash corresponding to the eigenvalue E dash is equal to E minus H cross omega. Okay, so H cap A cap square E is equal to E minus 2 H cross omega A cap square E. So there can be infinite number of eigenvalues, and these are the Dirac notation. So psi can be written as expansion coefficient C and N, then time evolution of state vector, your psi t is equal to summation n is equal to 0, 1, 2 n e to the power I omega n plus half t ket n, and then creation and annihilation operator. So E can be ket E can be written as ket n. So you can write h cap a cap n is equal to n minus half h cross omega a cap n, and you can write h cap n minus 1 is equal to en minus h cross omega n minus 1. So comparing the right hand side, you can say that a cap n is an eigenket of h cap with the energy eigenvalues corresponding to eigenstate n minus 1 in ket. So this still does not fix the normalization, as any multiple of an eigenstate is also an eigenstate of the same eigenvalue. So a cap is the lowering operator, and in this case a cap is also called annihilation operator, and a cap dagger is called a raising operator. A cap is lowering operator, a cap dagger is lowering operator, raising operator. A cap dagger raising operator, a cap is lowering operator, and these two will give you the annihilation operator and creation operator. Then the number operator, we define a cap dagger a cap as a number operator n cap. So you can write n cap n is equal to n n, and m n cap I is equal to m del m ml, where it is the Kroneker's delta. Eigenfunctions of simple harmonic oscillator, we have discussed it in Schrodinger picture. Now let us discuss in Dirac notation. So we have to determine the wave function for ground state of simple harmonic oscillator in bracket formalism, and the result will be the same as we have discussed in Schrodinger picture. So your n is equal to 1 by root over of n factorial a cap dagger to the power n ket 0. Then uncertainty product, del x is equal to root over of x cap square minus x cap whole expectation value of x cap square. So by you can evaluate it, and you can have expectation value x cap is equal to 0 and x cap square is equal to h cross by m omega n plus half, and your p cap expectation value p cap is equal to 0 and p cap square is equal to h cross m omega n plus half. So there are some terminal questions and some worked out examples. You can go through these. Then angular momentum. So you can have your angular momentum we have discussed now we did not have discussed, we will discuss here. Then spin angular momentum, orbital angular momentum, all these things we can discuss in this course. So what is angular momentum? Angular momentum, and what is angular momentum in quantum mechanics? Please have a recap of the things you have studied in classical dynamics. After that, we will discuss it in angular momentum, which is quantized, and we shall discuss how it is quantized, unlike in classical mechanics. Okay. Am I audible? Am I audible? Am I audible?
Yes, sir. Yes, audible.
So I think tomorrow we shall have a quantum mechanics class before 5 p.m. because after 5 you have some other class. So when you will free, you inform to the admin of this online class. He is present here, and he will inform you, and we'll have the class as per your convenience tomorrow, and we'll complete this course. Okay.
Okay, sir.
Thank you.